Okay, so we are going to look at inverse functions. Before we can look at inverse functions, though, we need a definition of a one-to-one function. And I believe we got it once before, but we'll get it again. In a one-to-one function, there is no repetition of y values. Now remember, a function cannot have a repetition of x values, but a one-to-one function can't have a repetition of y values. And you might recall for functions, we got the vertical line test. If we drew a vertical line and we touched a graph more than one time, we did not have the graph of a function. These, however, are functions, but they are special functions. They are one-to-one. No repetition of y values are allowed. And instead, now we have something called a horizontal line test. So let's take, for example, the parabola we've seen in our library functions, and I've drawn it back here. If I do a horizontal line test, if I draw any horizontal line, and I know that's not very straight, but notice that horizontal line touches that parabola twice. This parabola is not one-to-one because it fails the horizontal line test. Okay, so, oops, let me go back here. All right, so we can check a graph by seeing if it passes the horizontal line test to check whether or not we have a one-to-one function. So now let's get this idea of inverse. And before we get the official definition, let's get sort of an informal idea of what an inverse is. So I've got this function here, and it's just a set of points. And remember, we can check to see if it's a function because there should be no repetition of x values. So we have 2, 3, 9, 10. Now all of the x values are different. An inverse function really maps things backwards. So 2 maps to 5, but an inverse function is going to take that backwards and map 5 to 2. So we can very easily list the inverse here by just switching the points around. This becomes 5, 2, 4, 3, 8, 9, and 6, 10. So notice that I very easily got the inverse of this function just by switching the x's and y values. And this happens in every inverse function. The x's and the y values transfer. They switch places. All right, now let's notice that what we have left, the x values of 5, 4, 8, and 6 are all distinct, so it's still a function. All right, but let's look at the second one that I've got here. We've got a function, 2, 5, 3, 5, 9, 2, and 4, 7. And if we look at the x values, 2, 3, 9, and 4, they're all distinct, so it is a function. But let's do the inverse, and you'll notice that I'm not going to write the word function. It's an inverse, but it's not a function, as we will see. Let's switch our values just like we did for the first one. 5, 2, 5, 3, 2, 9, 7, 4. So notice that although I did an inverse, this is not a function because we have a repetition of x values, the 5 and the 5, which means that this original function up here was not one-to-one. And let's notice if we look, no repetition of y values allowed. There's the repetition of y values, that 5 and that 5. So this was not a one-to-one function, and therefore our inverse was not a function. So that's very important. To get an inverse function, we need a one-to-one function to begin with. So an inverse function, and I'm going to state here, which must be, and I should say an inverse function, which we will denote F inverse, has the property that when we compose it with its original function, we get x as the answer. And it doesn't matter which direction we compose it with. And I just want to make the note here that F must be a one-to-one function in order to get an inverse function. Okay, and of course our inverse function will also be one-to-one. All right, so we'll use this this detail that's in the definition in another video. I'll talk about checking to see that things are inverses by using the fact that we can compose them together and get x. but we'll come back to that idea. The domain of a function f is the range of its inverse. Now, if you think of what we did here to get these inverses, we switched the x's and the y's. So the domain becomes the range in the inverse. And in a similar fashion, the range of the function f becomes the domain in the inverse, because we're switching the x's and the y's. So if we know the domain and range of a function, we automatically know the domain and range of the inverse because they just switch. All right, so now we're going to actually find inverses from algebraic functions. So we've got a process. If it's 1 to 1, we're going to find an inverse. We're going to change f of x to y. We're going to switch the x's and the y's, and then we're going to solve for y. And at the end, we'll change our y to an f inverse notation. So let's look at this function, f of x equals 2x minus 1, and let's find its inverse. Now, it is 1 to 1 because if we think about the graph of this thing, this is in y equals mx plus b form, which means it's a line, and a line will certainly pass a horizontal line test. So let's go ahead and let's do our first step, change f of x to y. Second step, switch the x's and the y's. So my x is going to become a y, and my y is going to become an x. So looks like that. Now let's solve this thing for y. All right, so let's solve it for y. We'll just pretend that x is like a number. And to solve for y, let's add 1 on both sides. So add 1 on the right, add 1 on the left. So really, we can't add x and 1 together, so we'll just write it as x plus 1. On the right, though, our 1's cancel, and we have 2y. And then let's continue to get y by itself. Let's divide by 2 on both sides. And since my draw feature does not seem to be working on this computer, I'll just do this. So we're going to divide by 2 on both sides. So we get that y equals this fraction, and I'll go ahead and write it as a fractional equation. X plus 1 on the top and 2 on the bottom. And there's my inverse, but our last step says to change the y into the f inverse notation. So we're going to write f inverse of x equals, and I'll just copy and paste what I got right there. And there's our inverse function. Okay. Now I'll notice that this is just a notation. It does not mean 1 over f. It's a notation for inverse. Okay, so let's go to a second example. Let's find the inverse of this parabola. And we know it's a parabola because we can see that x squared in there and some transformation of our original x squared function. You'll notice there's a weird thing here. X is greater than or equal to 0. Well, what is that? Well, we need a 1-to-1 function in order to find the inverse function. So remember in the picture back here, we saw that a parabola is not 1-to-1. But what the x greater than or equal to 0 is saying is that we're only looking at the right side of the parabola. So the right side is 1-to-1. Or if we were only looking at the left side, it would be 1-to-1. So when we see that restriction, we can ignore it. All it's doing is making this 1-to-1 for us. So we can ignore it. It's just making it 1-to-1 so we can actually find the inverse. So let's go through our steps. Change f of x to y. Switch the x's and the y's. So we'll have x equals to y squared minus 4. Now let's solve this thing for y. So we need to get rid of the 4 first. So let's add 4 on both sides. And we get, move this up, x plus 4 equals 2y squared. And just like in the last one, let's get the y by itself by dividing our 2 out. So I'll do that on both sides. So divide by 2 on both sides. Oops. Divide by 2 here, and divide by 2 here. And now I have x plus 4 over 2 equals y squared. All right, and to get rid of y squared, we're going to take the square root. Now, normally we would have a positive and a negative square root, which would be two sides of a parabola that sits on its side instead of up and down like the parabolas we've been looking at. But since this is 1-to-1, we're only going to pay attention to the positive square root in order to keep a 1-to-1 inverse. So we're going to get that y is equal to the square root of x plus 4 over 2. And then lastly, let's change this to our F inverse notation. And you'll notice that as I've done this, I've always moved the F inverse to the front. We always want to write it in front. Functional notation always goes in the front. So we can always switch the sides as we're solving things. That's really not a problem. So there's our inverse. All right, now let's look at one more. Let's find the inverse of the function 2x cubed minus 16. Now, if we think about x cubed and its transformations, x cubed passes the horizontal line test. So we already have a 1-to-1 function here. Let's take it through the process. So we'll have y equals 2x cubed minus 16 when we change our f of x to y. Now let's switch our x's and our y's. So we'll have 2y to the third minus 16 now. Let's add 16 on both sides to get rid of our 16. And that will give us x plus 16 equals 2y to the third. And now let's divide by 2. And I will get, dividing by 2, we'll get x plus 16 over 2 equals y to the third. And just like we did with y squared, let's get rid of y to the third by taking the cube root. And then lastly, as we've been doing with all of them, let's put it in the F inverse notation. Well, I'll just copy and paste that. And there it is.